In this lecture we want to prove Nakayama's lemma, and this is very important. It shows up again and again. So let I be an ideal in some ring A and say M is an A module, and assume that I is contained in all maximal ideals of A. So this condition is generally written as that I is contained in the intersection of all maximal ideals of A, and say M is finitely generated. Then if M is equal to I times M, this would imply that M is 0, and if N is a submodule of M and you have such a condition that M is equal to N plus IM, then this would imply M is equal to N. So let us prove A. We will prove it by contradiction. So we have to show M is 0. So we start with M not equals to 0, and it is finitely generated, so we can choose a minimal set of generators. So say E1 to En is minimal set of generators, and we will arrive at a contradiction that we will be able to find a smaller set of generators, say E2 to En, which will contradict minimality. So our assumption M not equal to 0 would be false. So we are saying that M is not equal to 0, and we are setting M equals to IM. That is our hypothesis. So then from M you choose one of your generators, say E1, and then you can write it in this form: A1 E1 all the way plus all the way to AN En, where this AI lies within the ideal I because of the equality here. So this equality is coming right here, and here we are choosing E1, able to write it in this form. Now you bring this to left hand side, you have 1 minus A1 E1. It comes like this. So this equation comes like this. The first term has gone here. Now the only thing left is that we can arrive at contradiction and show that we have been able to produce a smaller set of generators for E1 only if we are able to show that we can invert this 1 minus A1. So that is inverted back here, and by inversion we mean that 1 minus A1 has to be a unit, and this is a unit precisely because it does not lie in any maximal ideal. So since it does not lie in any of the maximal ideals, so by the non-unit criteria this will become a unit because the non-units lie within the maximal ideal. Now to see that it does not lie in any maximal ideal is precisely because if 1 minus A1 lies in some maximal ideal, and you see this, then this A1, all these AIs are in this ideal I. So A1 will lie in some ideal I, but this ideal I lies within all maximal ideals. So all maximal ideals will contain A1. So if 1 minus A1 lies in some maximal ideal, it will also contain A1, and then you can see that 1 would also lie in that maximal ideal. So 1 minus A1 does not lie in any of the maximal ideals, and precisely that is why it is a unit, and therefore E2 to En generate M, which contradicts the minimality of generating set, which we said was from E1 to En. So part B just follows simply. You just modulo out N from both sides. So if you modulo out N from both sides, you get M over N is this ideal M over N, and now from here you can see M over N is 0, which is same thing as M equals to N. Now we come to the first corollary. So consider a local ring AM. So this M is the maximal ideal for this ring A, and it has residue field A over M. So this is our residue field, and say M is finitely generated module over A. Then we can say action of A on M over this, when you modulo out with the maximal ideal here, factors through K, and the elements, so this is more important here, elements A1 to AN of M generate M as an A module if and only if the following elements A1 plus MM comma all the way to AN plus MM, they also generate this M modulo MM as a K vector space. So these generators of M are in one-to-one correspondence with these following generators of this vector space here. So this direction is easy. If A1 to AN this generate this module M, then their images would generate this m modulo mm. So yeah, so this is just trivial. In the opposite direction, you say that a1 plus mm all the way to an plus mm, these generate this k vector space. So let's say n is a submodule of m and it is generated by a1 to an, and we are going to show that by Nakayama Lemma, then n has to be equal to m. So you have all these elements which generate this, and you take any submodule which is generated by these elements, then it has to be precisely m. So from if this is a submodule, so we can construct a short exact sequence. So n is injected into m, and then you can modulo out like this. So this is a surjective map, this is injective, so we can now write m as n plus mm, because this is submodule, this is just a surjective map, so you get a short exact sequence. You can write it like this. But now you can see this is same as this right here. Instead of ideal, we have mm. So therefore m is equal to n. M is equal to n, and that's what we wanted to prove. So again, you can see the correspondence between here and here. These are generators of m, and these are generators of this k vector space. So now we discuss another corollary. So this corollary gets used while discussing differentials or tangent space in algebraic geometry. So consider a Noetherian ring, and this is a local ring. So the ring is A, and since it's a local ring, it has a unique maximal ideal M. So A1, A2 all the way to AN lying in M, they generate M. It's the same way, this A1 to AN of M, now we are writing just the module M, they generate M if and only if this A1 plus M square all the way to AN to M square generate this vector space. So we are doing nothing, we are just copying corollary 1 to corollary 2 by replacing this capital M with our small m. So this is as a vector space over A over M. So here it was k vector space, and A modulo M is again k. So in particular, the minimum number of generators for the maximal ideal is equal to the dimension of this vector space. So yeah, so these generators here correspond to these generators here. So there's one-to-one correspondence. So again, this is just corollary 1. As I said before, we just replace m with this small m, and since A is Noetherian, this m is finitely generated. So you have these elements A1 to AM which generate maximal ideal, and then you can they will also generate this m modulo M square.